Welcome, space learners. In today's session, we'll tackle some fascinating numerical problems on galaxies asked in the National Standard Examination in Astronomy, NSEA. Let's dive into our first galaxy problem. Question 1. Analysis of the spiral galaxy NGC 1357 spectra reveals a strong emission line at 660 angstroms. Knowing the H-alpha emission line is normally at 65 and 60 angstroms, use the speed of light as 3 lakh kilometers per second and Hubble's constant as 70 kilometers per second per megaparsec. Choose the correct options. Pause the video and try to solve it. If you didn't get it, don't worry. To solve this question, let's first understand a few concepts. H-alpha emission line. Galaxies have a lot of hydrogen gas. When this hydrogen gas is heated by young stars, it glows in red light. This special red light always appears at the same place in the spectrum, 65 and 60 angstroms. We call this the H-alpha line. A strong H-alpha line tells us the galaxy has many new stars forming. Redshift. If a galaxy is moving away from us, its light gets stretched and looks slightly redder. This stretching is called redshift. Recession velocity. This is simply the speed at which a galaxy is moving away from us. Hubble's law. The faster a galaxy moves away, the farther it is from us. In short, farther galaxy is equal to faster galaxy. Now let's plug these concepts into steps. Step 1. Calculate the wavelength shift. Here, the line moved from 6560 to 6606 angstroms. That means the galaxy is moving away, denoting redshift. Take the difference between observed wavelength and H-alpha wavelength, which is 46 angstroms. Step 2. Calculate the fractional change in wavelength. Now divide this difference by the original H-alpha value, 6560 angstroms. This gives a fractional shift of about 0.007, meaning the galaxy's light is stretched by about 0.7% compared to its original value. Step 3. Find the velocity. Multiply the fractional shift by the speed of light. So the galaxy is racing away at about 2,000 kilometers every second. Step 4. Find the distance using Hubble's law. Divide the velocity by Hubble's constant. This works out to about 30 megaparsecs, which is roughly 100 million light years. Now let us evaluate the options. The velocity is 2,000 kilometers every second, so option A is true. The galaxy is redshifted, as explained earlier, making option B false. We calculated that galaxy is 30 megaparsecs away, making option C true. A strong HR emission line indicates active star-forming regions, not an absence of star formation, making option D false. Final correct options, A and C. Question 2. In the period luminosity relationship of Cepheid variable stars, a type 1 Cepheid has 4 times the luminosity of a type 2 Cepheid for the same period. The distance to the Andromeda galaxy was determined by assuming a Cepheid located in it as type 1. If it had been assumed to be a type 2 Cepheid, would the distance A increase by a factor of 4, B increase by a factor of 2, C decrease by a factor of 4, D decrease by a factor of 2? Pause the video to answer. Here are a few key concepts to help you solve this question. Cepheid variable stars. Cepheid variables are stars that brighten and dim in a regular pattern. The time it takes for a star to complete one bright to dim cycle is called its period. Period luminosity relationship. There is a direct relationship between a Cepheid's period and its luminosity, which is the amount of light it gives out. Longer period Cepheids are brighter and shorter period Cepheids are dimmer. Type 1 versus type 2 Cepheids. Type 1 Cepheids are brighter than type 2 Cepheids for the same period. In this problem, a type 1 Cepheid is 4 times brighter than a type 2 Cepheid. Distance and brightness. The brightness we see from Earth depends on both the intrinsic luminosity of the star and its distance from us. If we overestimate the luminosity of the star, we will overestimate its distance, and if we underestimate luminosity, we will underestimate the distance. Now let's reason through the problem. The astronomers assumed the Cepheid was type 1, which is brighter. If the star was actually type 2, it is 4 times dimmer than assumed. To appear as bright as it looks from Earth, a dimmer star must be closer. So, the distance would decrease by a factor of 2 because luminosity depends on the square of the distance. Therefore, the correct answer is option D. Let us check the next question, similar to first problem. Question 3. An astronomer observes a spectral emission line from a galaxy at a wavelength of 600 nanometers. The same spectral line is measured in the laboratory using a stationary source and is found at 500 nanometers. What is the speed of the galaxy toward or away from Earth in units of the speed of light? Is it A, 0.2 times the speed of light moving away from Earth, B, 0.2 times the speed of light moving toward Earth, C, 0.9 times the speed of light moving away from Earth, or D, 1.0 times the speed of light moving toward Earth? Pause the video and try to answer. The key concepts for this problem are spectral lines. Every element emits light at certain specific wavelengths, like its own fingerprint. By comparing light from a distant galaxy to light measured in the lab, we can see if the galaxy is moving toward or away from us. Redshift and blueshift. If a galaxy is moving away, its light is stretched to longer wavelengths. This is called redshift. If a galaxy is moving toward us, its light is compressed to shorter wavelengths. This is called blueshift. Recession or approach speed. We can calculate how fast a galaxy is moving by looking at the change in wavelength relative to its original wavelength. The fractional change in wavelength tells us the speed as a fraction of the speed of light. Now let's reason through the problem. The observed wavelength is 600 nanometers, while the laboratory wavelength is 500 nanometers. The wavelength has become longer, so the galaxy is moving away from us. This is a redshift. Next, we find the fractional change in wavelength by dividing the change by the original wavelength. This fractional change tells us that the galaxy is moving at 0.2 times the speed of light. Therefore, the correct answer is option A. Question 4. Inverse Compton scattering is when a low-energy photon is scattered by a very fast-charged particle and the photon gains energy while the particle loses energy. The frequency of the photon is multiplied by a factor equal to the square of the Lorentz factor of the ultra-relativistic particle. The low-energy photons of the cosmic microwave background, with wavelengths around 10 centimeters, can be scattered by ultra-relativistic electrons in radio relics in galaxy clusters. If those microwave photons of the cosmic microwave background with wavelength around 10 centimeters are on average scattered into the soft X-ray region with wavelength around 1 nanometer, what is the Lorentz factor for the electrons involved? The choices are as shown. Concepts we need to know. Inverse Compton scattering. A low-energy light particle, a photon, bumps into a very fast electron. The photon takes some energy and becomes higher energy light, while the electron loses energy. Photon wavelength and frequency. Wavelength is the length of one wave, and frequency is how many waves pass per second. Shorter wavelength means higher frequency and higher photon energy. Lorentz factor. This is a number that tells us how extremely fast and energetic the electron is compared to being at rest. It is dimensionless, no units. For our problem, the photon's frequency gets multiplied by the square of this Lorentz factor. What the problem says, microwave photons of about 10 centimeters are boosted up on average to soft X-rays of about 1 nanometer by electrons. We must find the Lorentz factor of those electrons. Use these formulas, gamma squared equals the final photon frequency divided by the initial photon frequency, which is the same as the initial photon wavelength divided by the final photon wavelength. To get gamma, which is the Lorentz factor, take the square root of that wavelength ratio. Substitute the values and simplify. The Lorentz factor for the electrons involved is about 10,000. Therefore, option A is correct. Question 5. The observed Doppler shift of spectral lines of galaxies is used to determine their velocity of recession from us using the formula shown. Spectrometry is expensive since the received light is highly dispersed and only a small number of photons are available in small frequency ranges, and so observations have to be integrated over long hours to capture the spectrum. In photometry, Light transmitted through various filters, which transmit light in a small band of wavelengths centered on given wavelengths, is measured. Photometry is much cheaper and faster. The hydrogen surrounding galaxies absorb light with wavelength below 100 nanometers. Hence, the observed brightness of the galaxy will drop drastically below this wavelength of emission. A galaxy was imaged through the UGRIZ filters in the Sloan Digital Sky Survey. The pivot wavelengths of these filters are 354, 477, 623, 763, and 913 nanometers respectively. A galaxy is visible when imaged through the last three filters. The galaxy drops out and is not visible through the other filters. The redshift of the galaxy, as determined by this dropout method, lies between pause the video and attempt the question. Short explanation of the ideas you need. Photometry and filters. In photometry, we take images through colored windows called filters. Each filter only lets through light in a small band of wavelengths around its central or pivot wavelength. If an object disappears in a filter, it means the object is very faint at those wavelengths. Hydrogen absorption below 100 nanometers. Hydrogen gas around a galaxy absorbs light that has wavelengths shorter than around 100 nanometers in the galaxy's own rest frame. That sharp drop is called a break or cutoff. Redshift effect on the cutoff. Because the galaxy is moving away, that 100 nanometer cutoff is shifted to longer wavelengths when we observe it. The observed cutoff wavelength is the rest cutoff multiplied by 1 plus the redshift. Dropout method idea. If the observed cutoff lies between two filter pivot wavelengths, the galaxy will be invisible. It will drop out in filters bluer than the cutoff and visible in filters redder than the cutoff. In this case, the galaxy is invisible in the U and G filters, but visible in R, I, and Z. So the cutoff must lie somewhere between the G pivot and the R pivot. Application of the concepts. The relationship between observed cutoff and redshift is as shown in formula. The observed wavelength equals the rest wavelength times 1 plus Z. To get Z, divide the observed wavelength by the rest wavelength and then subtract 1. Find the lower bound for 1 plus Z by using the G filter pivot. Next, find the upper bound for 1 plus Z by using the R filter pivot. Therefore, the redshift lies between 3.77 and 5.23. Correct answer is option C. That wraps up our galaxy numerical problems for today. I hope these step-by-step explanations helped you understand how astronomers measure galaxy speeds, distances, and redshifts. If you enjoyed this video and want to master more NSEA-style problems, make sure to like this video, subscribe to our channel, and check out the full NSEA playlist for more practice and detailed solutions. Keep exploring the universe, and I'll see you in the next video.